Hello everyone, my name is Dimitrios Nikolakopoulos and I am a graduate student at the University of Connecticut. This is joint work with Professors Stephen J. Miller and Anitha Srinivasan. Today I will discuss a classical technique known as Vieta jumping and show how it leads to a surprising connection with Fibonacci numbers. The motivation comes from problem 6 of 1988 the International Mathematical Olympiad, one of the hardest problems in the history of the competition. Only 11 out of 268 contestants solve it perfectly. A key idea in each solution is Vieta jumping. We study the related equation, the sum of a plus 1 over b and b plus 1 over a is an integer. By computing a few examples, we find that 1, 1, 2, 1, 2, 2, 3, 2 work, while 3, 3, 4, 3, 4, 4, 5, 4, 5, 5 do not. The natural question is whether there is a hidden structure behind all these solutions. Here we plot all solutions. Notice that the equation is symmetric in A and B, so the points are symmetric about the diagonal line A equals B. More interestingly, the points appear to lie on only two infinity branches. Connecting the points, we see two distinct curves. Our goal is to explain exactly why these curves appear. Say this integer k. We want to find the possible integer values of k, describe the solution set, and find the algebraic structure of this problem. First, we find the points on the diagonal line when a equals b, and the only points we get are 1, 1 corresponding to k equals 4 and 2, 2 corresponding to k equals 3. Next step is to clear the denominators and view that as a quadratic in a and b. We are at the case when a is bigger than b, and we recall Vieta's formula for a quadratic polynomial. The sum of the roots of a quadratic monic polynomial is the minus linear coefficient, and its product is the constant term. Then we have two quadratic polynomials. The left polynomial has an obvious root a, and let the other root be a prime. Applying Vieta's formulas, we have a prime is equal to kb minus 1 minus a. The a prime satisfies the same equation, and we can prove a prime is smaller than a. So we jump from a comma b to a prime comma b, which decreases the coordinate sum. Similarly, from the second polynomial at the right, we find the other root b prime equals ka minus 1 minus b, and we can prove b prime is bigger than b. So we jump from ab to ab prime, which increases the coordinate sum. I will not go through details. We show that starting from any non-diagonal solution, repeated Vieta jumps and coordinate swaps eventually lead to a diagonal solution. So the only possible values of k are 3 and 4. Conversely, every solution can be generated from a diagonal one using finitely many such steps. Here is an example for k equals 3, starting from the solution 234,90, applying Vieta jumps produce this chain. 234 change to 35, 90 to 14, 35 to 6, 14 to 3, 6 to 2, 3 to 2, and then we have the diagonal solution 2, 2. Reversing the process generates every solution from the diagonal solution 2, 2. Reversing the jumps, each new coordinate is determined by the previous two, which gives the recurrence an equals 3an minus 1 minus 1 minus an minus 2, with a0 equals a1 equals 2. The first terms are 2, 2, 3, 6, 14, 35, 90, 234 and so on. Subtracting 1 gives 1, 1, 2, 5, 13, 34, 89, 233 and so on, which are exactly the odd indexed Fibonacci numbers. This explains why Fibonacci numbers appear naturally in the solution set. The Fibonacci connection goes even farther. The GCDs of consecutive terms are closely related to Fibonacci and Lucas numbers, leading to the surprising result that the coordinate sum divided by the square of the GCD can take only the values 1 and 5. We can also view Vieta jumping from an algebraic perspective. After introducing the variables x equals a plus b and y equals a minus b, our equation becomes a Bell-type equation. The solutions are then described by the units of the quadratic field q adjoint the square root of k squared minus 4. In other words, Vieta jumping is multiplication by units in this specific quadratic field. Finally, let me conclude with a few generalizations and open questions. We can replace 1 by a parameter r and study the relation a plus r over b plus b plus r over a is an integer, where r is a positive integer. We saw the case r equals 1. The same ideals also works for r equals 2, but for larger values of r, the situation becomes more difficult. We can also consider versions with more variables, or replace the linear numerators by more general polynomials. In the 3-summand case with r equals 2 and k equals 7, there is no integer solution of the form s, s, s. The solution 7, 18, 40 has minimal coordinate sum, and applying Vieta jumping to the point 24, 176, 33 does not produce another integer solution. Here is the main theorem. We talk about only the case k equals 3. The similar results we have for the case k equals 4. Thank you very much for listening. I would be happy to answer any questions.